Dr. Frank Lehner. Dr. Frank, do you hear me?
Yes, do you hear me also?
Yes, I do hear you.
Ah, wonderful.
Please start sharing your slides and I will introduce
Yeah,
right
okay, I
now.
do that.
Okay, so Dr. Frank received his PhD in 1998. He worked as particle physicist at various collider experiments and in many research projects at DESY, Fermi National Accelerator Laboratory, and at CERN. Dr. Frank now is a chief of staff to support the board of directors at DESY and in charge of strategic partnership programs of the laboratory. He has an extensive experience in science management, administration, and policy in the framework of large international research infrastructures, working also on the strategic positioning of the laboratory at national, European, and international levels. He started the Building Bridge initiative at DESY to embark on a joint energy science partnership between Europe and the Middle East and North Africa for future sustainable developments. Dr. Frank also coordinates the German science diplomacy activities to support Sesame in Jordan. So, Dr. Frank, please, the floor is yours.
Yeah, thank you so much. Sane, do you see now my full screen or this display window?
Yeah,
I'm
yeah,
not
we see it in presentation mode.
the full screen. Yeah, okay, wonderful. Thank you so much. Okay, so yeah, it's a pleasure for me to talk to at the School for Synchrotron Light Source in the applications. So normally, if you are at this school and workshops, you hear a lot about scientific results, about data, about synchrotron radiation techniques. Less visible and less discussed at these meetings is the way how research infrastructures and also synchrotron radiation sources, light sources shape economy, how they generate also and improve the skill sets of the people, how they contribute to capacity building and also to solve problems in the society and also contribute to also political agenda and agenda setting, which is set forth by the governments and by the ministries. And this is a thing which I would like to discuss today to see how deep this field, how wide is also assessed in the moment. So you will hear a little bit today about socioeconomics at large scale research infrastructures with a certain focus on light sources, of course. A little bit about me, it was already mentioned. So I worked at various labs. I have here some experience also in the research management. My employer is DESY, the German electron synchrotron in Hamburg and also in south of Berlin with two sites. We run a lot of research facilities and accelerators in astroparticle physics, photon science in particular, but also laser plasma accelerators and data science centers. Our future project is Petra 4. This is a huge initiative, a huge project. We hope that this year we get funding for it. There was a lot of campaigning done politically, political advocacy, discussing also reasons why we need this in Germany. It's now on the prioritization roadmap by the German government, which is quite good. We are talking about a 1.8 billion euro project, so that's not really a little money, it's really a lot of money. And so we are quite successful in all our campaigns. So I'm engaged at Sesame for many years and also strongly in various projects, EU projects and other projects in support of Sesame. So what do I want to show? A little bit back in history, why excellent science is a key, of course, at facilities, but it's for justification and for arguments to get funding for a new facility, not fully enough. I will tell you a little bit about the basics in socioeconomics and impacts. What does it mean? How do we address this? How do we monitor and assess it? And I can show some examples of various impact areas and some of the case studies. Now, if we go back in the history and we look at maybe one of the first early research infrastructures, at least on the European side, this was an observatory in the 16th century by Tycho Brahe. He was a Danish astronomer, extremely accurate measurements, which he was providing with his observatory on the island of Ven, called Uraniborg, and his data and his experiments were basically the base for the Kepler law, for the rotation of the planets around the sun on elliptical orbits. And so at that time, it was, let's say, relatively easy to get the funding. You need the king for it, yeah, or a queen. So there was a stakeholder dimension which was exactly one. This was a decision maker, the King of Denmark, in that case King Frederick II. There was one funding agency. It was the treasury of the King of Denmark who gave the money to Tycho Brahe. It was one customer because all results that he produced were given to the King of Denmark. It was a communication only to one person, the King of Denmark. Justification of the investment of this observatory. You see here a picture of it. Tycho Brahe sitting here and looking at the stars was probably relatively easy because he promised something, but he had only one person to deal with, and he was also, of course, dependent on the king. So when he died, King Frederick II, the new king of Denmark, Christian IV, forced Tycho Brahe to leave Denmark because he got upset for maybe a wrong prediction of stars. I don't know. So this was relatively easy with the stakeholder dimension of one. Now, if you look at modern research facilities, even if they are built in an international environment like Sesame, but here I took an example from Hamburg, that's the European XFEL. It's not a synchrotron radiation. In fact, it's an X-ray free electron laser. So it produces ultra short X-ray pulses, 27,000 per second with an extremely high brilliance. And here we have something like 12 countries participating in that. So all these stakeholder dimensions become higher, it becomes more complex. The justification of the investment, if the various member countries are also committing to it, is much more complicated. And you need, of course, clearly different ways to do it. Now, if you go back a little bit also in history and look what the arguments were for large-scale facilities over the last, let's say, century or so. So investments in big science and in big facilities, it came down in the 40s and 50s, so way beyond Tycho Brahe, so after the Second World War. So these were the birth of the modern lab. So it came out Los Alamos from the Manhattan Project. Then there was the French nuclear program, later on the Apollo program by NASA, but also the big labs like CERN and others profited from that. So this was the governments wanted to have big science laboratories, big science done, focus the people on a certain agenda, have also top-down agendas related to national security and national ambitions. Then there was a phase in the 70s, 80s, and 90s where it was basically by the policymakers driven by scientific benefits, curiosity driven, diffusion of technology. Then came all the political framework of the grand challenges, the societal challenges, climate crisis, health, aging society, SDGs, which is still valid and absolutely relevant for us to address these. And now I have to say what we experience also in these times over the last, let's say, 10 years is more or less a focus also on technology sovereignty in a very multipolar world, I have to say, in a complex world. Where emerging technologies are becoming now more central as an arena for having influence and strategic advantage. So all this is a little bit of a discussion right now where you, if you think of a facility in a country, maybe with other member states also have to address this to some extent. I mean, there are new political frameworks, new political settings, and to some extent we have to find also, apart from the scientific excellence, we have to also find somehow ways and avenues to address these issues, because these are the policymakers, the government, who are actually defining at the end also where the money flows. Now in Germany, and this is a relatively recent example, we are now quite much into this framework of a high-tech agenda. So this is now shifted a little bit to technology. Maybe 5 years ago, it was really the grand challenges and societal situation. Now we have to focus on high technology. This is a strategic investment program. Our new facility, Petra 4, will benefit from that a lot. We will try to really align our experimental capabilities according to the high-tech agenda. It focuses on key pillars and on certain areas which are maybe not really a new invention of things, but these are the normal things what people would address in modern economies and societies. In particular, what is now coming up more and more is the fusion part, so where you really somehow look also at synchrotron radiation facilities or even at X-ray free electron lasers, contributions to fusion science, to plasma matter interactions or so, because there's a strong drive in the moment worldwide going on in all areas, Asia, in Europe, in Americas also, to set to fusion for the next energy. So now these are rules which have changed over the last years. So political goals, they are not always stable, and they are aligned with what is now in the according decades really the challenge. So it could be sustainability development goals, it could be agenda, high-tech agenda, it could be sustainable transformation, digitalization, technology sovereignty. So this is a framework what the politicians are setting, and the rules of the game are changing. So if you want to really get a justification for a large-scale facility, and if you really want to also convince policymakers and governments to say, yes, this is worth the investment, we have to also do that and play this game. And we have to point out that there is excellent science, of course, but this drives a lot of other things. It drives innovation, it drives also the economic growth, and it contributes to technology sovereignty. It contributes to some certain welfare, whatever is in the moment the key in the national or international political arena. So, and governments and also funding agencies, they are also, of course, requesting now a proof of evidence of this return. So they want to see what is coming out of this money. And these stories or narratives on successes are nice, but they are less and less going. It's more complicated in times of financial restrictions. So you have to somehow rely on demonstrated impacts, on tangible impacts, and you need to monitor, quantify, and document these evidences wherever possible, also at research infrastructures. If you are in the laboratory, the management on owner of a facility, you have to really look into that, how this is actually then monetarized, and also how values are coming out. So what do we know about all these impacts apart from the scientific excellence? So science has, and this we know for many, many decades now in literature, in economic research, science has a profound impact on economy. There's a clear and well-documented correlation between R&D expenses and spending and the GDP growth. This is over many decades verified and validated. And this is a plot which I took from a think tank paper, TEA, from October 2024. Here's the link. And this shows a little bit this the way how on the horizontal scale the GDP spending and also the GDP, the annual rate of compound growth, and the investments in R&D correlate. And then you see countries who are spending a lot. Here, Estonia in R&D relative to the GDP, which have a quite a large driver. So, and without any of these signs, also at large scale facilities, we would not have these technologies which we rely on, let it be lithium ion batteries or Wi-Fi or any materials also of high strength and ductility or any microfluidic cooling system. So it's clear that there are tangible impacts, that there are some outcomes out of science, and that the socio-economic impacts of this public research sector, this is really uncontroversial and has been documented extensively, and there is a lot of papers about this. So for instance, a seminal paper was done already in the 2000 by Salter and Martin on the economic benefits of publicly funded basic research. That's really one of the base papers of all these economic benefits, which try to really categorize the various effects of socioeconomic impacts coming out of research. Now, there is for research facilities also over the last 20 years or 25 years, a lot of studies and a vast literature which you can find. So many studies which looked into details for various facilities all over the world, and who presented also cases how the economic impact was related to a facility, either if a facility is being planned or proposed to a government, or an existing facility has operated over the last 10, 15 years, and the funding agency or the government wants to see, so what was really the outcome out of this 15 years or so of public spending, what was really at the end the return of the investment. Now for Petra 4, what I mentioned before, in particular the existing facility Petra 3, we did also such a study. We did it together with the Fraunhofer EASY Institute, which was an ex post analysis, so looking really back over the last 12 years of operation of the third generation hard X-ray source, and we did also some projections and ex ante analysis to Petra 4 as a fourth generation ultimate low emittance source. And it was actually very important, yeah, in the process last year, in the discussions with also politicians or so, if you sit also in committee meetings and have parliamentary hearings and organize also breakfasts, events for the politicians, that you see, I mean, they look really at these numbers. Yeah, it's actually frightening sometimes to feel that also that not everybody is interested in science and in the fascination. Sometimes they want to see really the numbers. They want to see so how many jobs are created and so on and so forth. And that's why you have to be prepared for these things. And that's why such a study is also very important. Now, what are these impacts? So how do we really address these and how do we approach this impact? So what is our understanding of this? So in principle, a measurement of an impact, if something has an impact to something, it needs in theory a measurement of the world or the surrounding environment with and without this investment or this input or this intervention. So in fact, if you look at this graph, we have here the time t, and there is at time t0, there is some certain effect. It could be an injection of funding, it could be some intervention or so, and then it moves on either without this effect or with this effect. And then the difference is just according to the time, it's just the impact. So this is in principle the idea, very simple. However, there are challenges because we don't know if there's a direct one-to-one relationship between any investment and an impact. We don't know if it's a direct or unidirectional relationship. It could be nonlinear, it could be multidirectional. So we also don't know what portion of the effect, if we invest in something, should be attributed solely alone to this initial input. There are, of course, interferences with other facilities, maybe with the surrounding ecosystem which is being set up, with some other research centers which are growing around, or universities around these research facilities. So sometimes it's difficult to separate it out and say this is really clearly due to only this facility. And of course, the definition of appropriate indicators, proxies, or so, all this is highly relevant. And then the time scale, at what time should we measure the impact? So there are typically, I mentioned it a little bit, the two terminologies which are quite often used in all these studies, ex ante and ex post. So ex ante means forecast. You have to justify the investment decision. It is a prediction thing. And ex post, you look back, you have maybe real data of a facility, you have real numbers for the number of PhDs which have been trained at your facility. So this is in fact for reporting, for accountability, search for improvements in optimization. So these are the two ways of this study. So now you need, of course, to address these socioeconomic impacts, you need also a conceptual framework. You need a methodological framework which defines also the various impact categories and also the way how you want to measure it. So it depends also, of course, on the way, what is your stakeholder and your target group and your audience. But at the end, there was a project within the Horizon 2020 RI path called Chartering Impact Pathways of Investments in Research Infrastructures. It was led by European Future Innovation Systems EFIS Center. So we had a bunch of research infrastructures participating in this. It was CERN, ALBA, DESY. It was in the time 2018, 2020. So we at DESY also participated in this. And I think it is a very nice framework, a conceptual framework, which was developed for socioeconomics, for impacts, and it also, the philosophy was to define concrete pathways to impacts, trackable pathways, so that people who do such studies can also get a guidance how such a pathway from some output can go and turn into an impact. And they also provided then later on in follow-up projects some impact assessment toolkit. And this is what I would like now to talk a little bit about that over the next 2, 3, 4 slides over this RI path before I go into concrete examples just for illustration of this. So the RI path was basically setting up a model that you say an impact comes out of a certain activity at a research facility. So a certain activity like doing direct research or producing a publication, a paper, so taking data and analyzing something, this is your activity. You need, of course, resources for it. So basically the money or the person power, manpower, which goes in. But then out of this activity comes an output. And here I think I would really like to point out these terminologies here that we do not easily mix it, and that we in future, if we also address these various terms, that we really have a good definition of that. So we distinguish in these discussions on socioeconomics quite often output from outcomes and from impacts. And I would like to explain it in that model. Yeah. So really out of an activity comes an output. This is just the idea of this. This is something what you have under your control. There's a direct responsibility of the researcher, of the research management, and so on and so forth. An output then is an immediate direct effect. And the product, it could be a publication, for instance. A publication is an output of a facility, it's not an impact. And also the so-called impact factors of journals are a little bit misleading in strict socioeconomic terms. So output is an immediate direct effect, and products attributable to an activity performed at a research infrastructure or by a research infrastructure staff. It is by the scientists. Outcomes, output comes into an outcome, either short-term or long-term, if others become aware of it. If others are using your publication or citing your publication or using your data or your product or your software or your license, and then they generally occur in the short to medium term. And then there are impacts. Impacts are then really changes of this after some certain time, which occur in the society, the result from these outputs and outcomes, and they typically occur in the longer term, and they have really then a more profound change also than the immediate outcomes of this. And the strength of this RI path is also of this conceptual framework that you define various pathways from activities via outputs to outcomes, and then also to identifiable effects and tangible effects in the economy and into the wider society. And this is what I will talk about. So it's also a little bit of an interesting note here, so that they used a tree model, so really like a tree, that they say that these impact pathways are not always linear. You cannot say this activity produces this impact. So it is not linear and it branches out. It's like an evolving web, a branching tree. It's not a straight line. So at the end here, the base is really your resources, activities. You have the various outputs from your facility. So basically your scientific output. These are the data, the publications and so on, presentations in meetings and so on. And then it branches into outcomes. Yeah. So others take away, take note of this, are using it, are citing it, and so on. And then comes later on really the impact, if it goes into a product, if it improves any process or so in industry or whatsoever. Yeah. So this is the idea of this, and I think they have a very nice guidebook, and I have given also the references of this in the website, and one can really look into that. And it's a very nice description of the way how one can distinguish something from an activity into an impact. So important here is indicators. Indicators capture the activity and the output, and they are really crucial. I mean, you need a lot of set of indicators which are useful, which need to be easy to measure. I mean, indicators for activities and for output, easy to collect, user-friendly, reliable, meaningful, comparable data should ideally be collected over several years in a constant manner. So this is what one would say, this is more or less impact monitoring over many years. There are quantitative indicators like the number of PhD students trained or the licenses or any income or revenue or so, but there are also more qualitative indicators to describe a certain status or a situation. Yeah. And clearly, one needs to somehow select this and keeps track of these indicators and then works out also some socioeconomic metrics or this. So if you would like to look into that, so there's a catalog at RI Path, an extensive catalog of indicators which is given on that website. It's almost an interactive tool. You can also filter a little bit what kind of impact area you would look at, and I come to that in a moment. And then you can somehow get an impression how long these lists can be. Not everything of these indicators makes sense for all type of facilities, but one has to really look into that a little bit. Yeah, what could be meaningful. So we DESY, we have also central reporting unit here for our Helmholtz Association and also for the ministry. A lot of these indicators are anyway captured normally. Yeah, they are basically scientific indicators, and we have to report them anyway every year or so. Yeah. So now we have all the indicators. We have understood a little bit what we can measure at a facility. So how are now really the four areas of impacts what we can really imagine? So where does really manifest, where does an output and an outcome of a facility really manifest in society? And what does the society also and all the socio-economic surrounding, do they benefit really from it? And there are, my understanding, also four main areas which we can discuss now, four main areas which are also proposed in this project, RI path guidelines, which are of relevance. Of course, science and scientific excellence and scientific results is always a key, that's clear. And you have to design also a facility that you produce good science. But at the end, the impacts go into human resources. So where you really build a better workforce, where you actually produce the next generation of researchers who might go maybe to industry or so. The second is the impact on all what is economy and innovation, where you increase innovation, where you say you would like to have a startup ecosystem around you, where you would like to do technology transfer, where you would like to do also some impacts on the local and regional economy in partnerships, for instance, with industry companies and so on. Third one is the society. So what do you bring as a new solution to the society? For instance, to the grand challenges. Yeah. What is the benefit of knowledge for the society in different domains? How do you contribute also to the public awareness of a problem, climate crisis, for instance, yeah, or to the awareness of science per se? Yeah, cultural impact, social inclusion, environment. So this is basically the area of society. The fourth one is to the policymakers. So what do you contribute really to make policy and decision makers their life easier? Science-based, evidence-based decision making. How can you contribute to standards in nanoscience? Yeah, or quantum technologies is a field where you need standardization, you need norms. Yeah, what do you do there? International cooperation. This is, of course, extremely important in the current world. Yeah, science diplomacy, international relationship, keeping also facilities like Sesame alive in a not so easy regional setting in the moment. Yeah, sustainability, ethics, and trust in science. So these are the four areas, and I would like to go in the next slides a little bit through these areas and show some examples here to help you to grasp this a little bit better and to understand it also a little bit better. So let me start with one, human resources, human capital, sometimes also coined. So these are the effects if you have a facility, and these research facilities, synchrotron radiation sources, but also others, they are really a magnet and a talent hub for researchers. They attract a lot of good people, excellent people who are coming, doing research. There are a lot of opportunities for young people to do their research and to support their excellent research. And they create a lot of competences and skills. Skills which come because they work in multidisciplinary teams, skills because they work in international teams, yeah, skills because they work in frontier and high technology environments. So all these are things which can be traced back also to that environment, to the work at and with these facilities. And there's a lot of capacity building through training and learning at RIs. If young people are coming, they are so fascinated also. They like to work in these larger teams and in these interdisciplinary teams, and they are also attracted by the way how such a lab is also operating. Crucial, of course, cooperation with higher education institutions, universities. And it's also for natural science, not only physics related, but also chemistry related. So these natural science related industries are for the society major economic contributors. So whatever you do in terms of educating and training young people, this is really a big asset. And you can look into that also, how much a PhD student is worth to the economy at the end. This is what some people are doing. Yeah. But we have looked, for instance, at impacts of PhD students. This was a study which we did, a big survey of 1,200 students, which did between 1973 and 2014 their PhD on the Doris storage ring, which was actually a collider first in the 70s and turned into a synchrotron radiation machine, one of a pioneering facility. And so we visualized the career paths of these people who were partially 30 years later after their PhD, and looked into the competencies and skill sets. And we found out also that this is really fantastic, yeah, in the way how they contributed also part of their career later on, even if they worked in some other sectors, to the experiences gained during their research work and to their work at the time at this facility. Also, a very recent study is the study from ESAF, so the European Synchrotron Radiation Facility, done by Technopolis. And commissioned by the United Kingdom Research Council. So this was a look at the UK involvement in ISAF to understand really what do their UK users and UK students learn when they go to the ISAF. And they also did a survey and questionnaire. It's interesting to really look into that result, so that 90% said there must be at least a small positive impact on them, and that the listed skills and capabilities, teamwork, problem-solving skills and all this have really improved of this. So this is quite impressive, I think. So it's really good that these facilities also help in the developments of personal skills of people who get better here and increase also their competences. 70% in the survey said also of the respondents said that they highlighted that working at ISAF, so in this environment, international environment, had improved really their ability to work in such an international collaboration. So this is good data, I think. So there are many surveys like this, and this is also extremely helpful to work out these things and to look into some results from this survey, and really to make sure that and clarify this also to the politicians, that there is an enormous contribution from these facilities in shaping also and training young people internationally, nationally, and so on, and to improve also their skill sets. And this is important because it directly pays also into the economy. The other one is impacts on economy. So this is the second area now after leaving the human capital. So the main tool here is what people are normally doing, input-output analysis. So that's a quantitative method to estimate the economic impact of an organization or project or a facility on its surrounding economy. How does spending, either in capital cost or in operational cost, translate into regional or national wealth and growth, yeah? Or put it simply, how much dollar is generated in the economy if I invest a dollar in science. Yeah, very naive. But this is at the end what the politicians want to know. And then sometimes they come up with something like $1 generates $25. Yeah, it's a little bit high, but there are many studies for these regional studies also with quite substantial content, and there is also a literature about this, and I come to that in a minute, yeah, and compare a few facilities. So the core idea of this input-output analysis is like you look really at the money trails, at the path of money. So your input is your investment in the facility. The analysis begins with this input, and then you look because you have people on board, you have staff, these are your salaries, your personnel, your wages, you have the operation of the facility, and you have the procurement of goods and services, like you need high-tech equipment, you need instrumentation detectors. And so this is basically then, later on, these are the direct effects, and then indirect effects are now through multipliers. So this now goes into the economy and ripples through the economy. So you pay to a supplier a new measurement device, a Keithley picoampere meter or something like that. Yeah. So this basically creates also some certain value. And there are, when RI buys specialized equipment, for instance, some optical equipment or so, mirror or so, that firm then pays its own employees and suppliers, creating further economic activities down the value chain. So there are some clever ideas how to quantize this, how to capture this. Typically, these are regionalized multiplier effects, also for different sectors. Civil construction is maybe not so much than the high-tech equipment. IT data also is always higher, electronics, semiconductors also. It depends also a little bit how the economy is structured, what sectors are there, and so on. But clearly, the more high-tech component you have involved in your facility, the less concrete, the better it is, of course, in terms of economy. If you look at the economy, which has some vendors who are strong in that, yeah. And so this can be looked at. So there are direct, indirect, induced impacts. I quickly touched it a little bit about it. So direct is coming immediate from the jobs and economic values, indirect impacts, and also induced. So there is still an economic boost when also the suppliers who also get a salary, yeah, and they live because we are buying services and goods from that supplier. They also have salaries and they also spend it, yeah, because they live in the area or they go to the movie theaters and so on and so forth. So, and typically what people find out typically in these multipliers are, I would say, yeah, 3 or so, up to 3. Yeah, I mean, I've put here 1.2 to 2.5, can be sometimes higher also, but these are typically the multiplying effects. Yeah, and then there are long-term supply effects of an RI that gives additional boosts, and they are much more complicated to capture and much more complicated really to quantify. They need econometric studies, long-term ex post studies, case studies. This is what I have here on the right-hand side. So this is really competitive advantage, for instance, of a company who is using X-rays, for instance, in pharmaceutical applications, in developing drugs, and at the end they develop a new drug, a new a molecule or so who acts as an inhibitor or whatsoever, and then it's on the market, brings it on the market and makes really a business case. So these are long-term effects, competitive advantage effects, which cannot be so easily quantified. It needs own case studies, and you can maybe value and also monetize the market of this. Yeah, and there are some approaches to do it, but at the end, so at the end, one needs probably for that really individual case studies or so for that to look into that and to really make it a strong case out of this. That, for instance, certain discoveries and new drugs also really bring a lot of new advantages also for the market. So Some examples here for our Petra 3 project. In 12 years, we have about this factor of 3, almost 850 million euro, which was really invested into construction and into operation. So we generate out of this 2.25 billion euro. Triumph, for instance, says they increased the Canadian GDP by 490 million Canadian dollars. So they claim this is a factor of 1.7 of this investment. They also work out how it's distributed in British Columbia or in the rest of Canada. So, and then Argon, for instance, based on, they have a factor of 2 something, 2 point something. Also, they give some economic outputs. There are many studies of this. A recent study is actually a compilation of various RIs done by a G7 group, from countries. Looked at the impacts of 57 research infrastructures in G7 countries. You see the distribution of these facilities all over the world, with the various sites here. And then they try to analyze this data by their own. They use their own multiplier effect. So these are not 57 individual studies. It's not a meta study, but they took the data, the expenses, investments from 57 facilities, and they did their own economic analysis, but taking into account local and regional multipliers into account. And so typically they have a minimum multipliers 1.2, average is for them 2.6, and maximum is something like 4.5 or so, So, but it's not 10, it's not 20, it's not 30 for this effect, So this is typically what you say. So if you say $1 in research generates at a facility from the demand side something like $3, then I think you are on a safe side. If you consider long-term effects, agglomeration effects, it can be even much more. But this is in the moment the narrative what people say, and I think that's also fine. So I would like to also discuss one interesting study from the Diamond light source, so the UK light source, which was issued also 2021 by Technopolis. So this is one service provider of such studies. It's a company, which has several branches or so with clever people. And so they looked also in the Diamond data. Diamond was built in the time 2007. The project started. It was the successor project of a previous synchrotron facility, which goes back to the early 80s. And so they say 1.2, let's make it here, 1.2 billion investment in the facility, British pounds. And at the end, they found out a cumulative monetized impact of at least 1.8 billion based on the evidence captured. So that's already something. But they do not stop here. And this is why I think the study is of interest. They also try to monetize and understand also the economic value, not only of the spending here, of the people, direct, indirect, induced, but they also try to really somehow estimates further effects, what this facility has produced. So it's actually a very nice infographic here, a sheet which gives some key figures from that facility, and which is for politicians, if you present it like this, extremely impressive, really extremely impressive. So, but they also say, for instance, and that's very interesting, over 10% of the publications generated at Diamond, also at Petra 3, it's similar, at ESAF also. So 10% of the publications coming out of synchrotrons are cited in patents. So that's already good. So you have patents, you have the application of patents, and they cite literature. And so 10% of all the output from a facility comes at the end into patents. And if they take the patents, and this is what they did, here at Diamond, if you take the patents together, and you say, okay, what is the value of this patent? You can also, I mean, somehow estimate this, by some numbers or so. They come with a number of 11 billion, So the patents worth, which are citing their facility, their data also, it has alone an economic value of 11 billion. This does not mean that that's a direct impact. There might be other references as well, but it only says that there is a good contribution, yeah, from light sources to patents, and that this plays a massive role, and that also these patents who are using data or information or results from light sources, that they have an economic value. Or the global structure biology hub. So normally if you do macromolecular protein crystallography and you solve the structures out of the many, 150 or 160,000 or so. So Diamond alone was doing 13% of the protein structures in 2018, and they also looked into that, how much it is if you compare it to drug discovery things, then massive user network, education pipeline, and so on. We just discussed this before. So that's interesting, impressive also how you can concentrate and reduce also an impact into various areas in a short infographics and also in a short illustration here, and you show it to politicians, and they will really, I mean, I will love it. Yeah. Okay, leaving now economy, the field of economy and the impacts going now to the society. So where do you have benefits to the society as a whole? Also, economy is part of the society, of course, but how well do you address the societal challenges? Yeah, how do you contribute to solving the kind of societal challenges? It's an own area where you have to look into also impacts and how your facility contributes to this. So this could be direct through research contributions in terms of sustainability, health, climate, biodiversity, mobility, and so on. And synchrotron radiation publications are full with these areas. Yeah, indirect how knowledge also leads to innovation and also to companies who are also solving then problems and developing solutions to this. Communication, public awareness, outreach, and social cultural inclusion is in diversity, environmental impact. So that's, for instance, a graph which we produced for Petra 3. So when we looked into our publications or so, publication database, we did a mapping to the sustainability development goals. So this is German, unfortunately, but the color scheme and the way how this chart is done, this is the SDG. These are the SDG goals, and this comes quite often. So this means that many of these publications really contribute directly to SDG goals. And that's also impressive to show that and to say that 80% of our publications coming out of our facility can be really directly attributed to one of these SDG goals. Yeah. So that's quite interesting and good, and it's also a very good narrative or so, and a key message to these politicians. So whenever they fund a synchrotron radiation source, it's not for really nuts. Yeah, it's paying really directly into the sustainability development goals. Then there are some impacts to society as a whole. So we all know about the pandemics and the impact, the big challenge to develop the vaccines, yeah, or to understand also medication if people had COVID-19 or so, or even the fast tests, yeah, to look into that. And there was really the light sources and the through LEAPS, the organization which is basically organizing all European light sources plus Sesame as an associate member. There was a very quick position paper which came out in May 2020, looking into that and also opening access, yeah, to this research. For instance, at DESY during the COVID-19 pandemic, we also opened our beamlines for some research. We did some X-ray data, some work here, experiment work on a massive screening project, which was also then later on published, where we screened various drugs which are coming from a repurposing library or so to find really some binding molecules for the main protease or so. And this was somehow a big effort, and it was good. And many other labs also had these efforts, and I think it was worthwhile to do it. And it was also good to have work there because at the end also medication, drugs, and also vaccines could then be relatively quickly also produced and generated also for the market. Now, other impacts on the society are outreach, public engagement, of course, tours, visitors, which you have to do, school labs. So we have to somehow, these are also examples from our lab where you somehow say, I mean, you show these people your facility, you make them interesting for science, you make them even interesting in studying physics or chemistry or so. And this is something which you really also have as a very important value also for your lab, and that's something which also counts directly into all the socio-economic impact. Citizen science is something what a lot of astronomers are doing it, observatories or so. Yeah, I mean, the mother of all citizen science project was the SETI search, where people use their CPU from PCs or so to look for extraterrestrial things. You can do it now in biology as well, molecular biology, to look really at some structure solving of a complex structure or so. But these are actually quite important to motivate, and it's always good to have cases there and to collect this and to present it also in discussions with stakeholders, also with government and ministries about this, because that's some direct return. Then political impacts, impact on policy, that's the fourth main sector. So research infrastructures really improving the science policy interface, helping to make evidence-based decision making. Yeah, how you can support scientifically policies or policy development. Yeah, how you can give expert advice in support of public policies. Yeah, how you can work on standardization and regulation in emerging technologies, which are basically coming up. Yeah, in quantum technologies, also nanotoxicology. Science diplomacy, trust building. So this is, of course, extremely important in these times. So how can we build bridges between communities, societies, and nations through scientific cooperations? Of course, flagship example is CERN. Yeah, after the Second World War, the bringing people together here for peaceful research. ICTP, where we host this wonderful workshop. Yeah, is another example. And of course, Sesame in the region in the Middle East, which plays also enormous role for the science diplomacy. And this is a huge effect also for trust building, for the understanding of the various communities. Then impact on confidence and trust in science. So can we really somehow demonstrate and show also that trust and the belief in science is increasing also by talking to the public and to also make outreach events. Yeah, so science matters here and has a central role in this public debate. So again, I have to go back to the COVID pandemic. So we saw a drop in the public perception of science, not in all areas in the world equally, but these are data from the US now. So where we see this dip, yeah, after the pandemics, where maybe not everything was great in the discussions or so, but this is an important thing, yeah, to bring it up again and to have really the society also um, back again in saying science is really an important thing, and we have to trust also in our scientific endeavor, in our scientific infrastructures, also in the way how we do science and how science is also pursued. Yeah, so that's absolutely important. And any decrease in trust and also in the perception of science and also the discreditation of scientists in public is really an enormous problem now and leads to negative consequences. Yeah, definitely. So yeah, these are, as a quick summary, take home message, these are the four from this RI Path project, the four main areas where you at the end discuss, document your impacts coming out of the facility, human resources, so the way how you create capacity in the minds, in the brains, in the people, in the talents, the societal impact. Yeah, what do you really contribute to the grand challenges of our society? The economy, innovation. So this is what governments like in the moment. Yeah, technology sovereignty, economic competitiveness, advantages, and so on. But we have to play this, and we are driving this a lot. Yeah, and there are so many good examples from that out, but also in the political arena. So how can we help also politicians to make the world better? How can we give them scientifically based arguments, evidence-based decision-making or so, where can we also contribute as a facility to that. Yeah, so these are quite important areas. Everybody has maybe its own taste and feeling what is the most important, and it might change also depending on the societies and on the political frameworks, but that's this tool. So helpful is, of course, exchange with other facilities at the ERIC Forum. So these are the European Research Infrastructure Consortium centers, a forum of ERICs, which are organizations. So DESY also is hosting one ERIC with a Cherenkov telescope array. And there are 24 in Europe, which has been founded in international cooperation. They also look into these, they share best practice, identify common grounds and challenges, help to build also common framework that other ERICs can identify and measure socio-economic impact. So there's also quite some best practice examples and good literature about this, and also a lot of exchange on these. We also did a workshop, it's already now 7 years ago, at Cyprus and in Turkey on Sesame, and also on the socio-economic impacts with young people, users from the Sesame facility. We wanted also to know how they see in their countries, and also through the work of Sesame, what they see as important. And so we did very interesting discussions, had good workshops or so with experts, with young scientists or so, and at the end also formulated some guidelines or so, which are still good, yeah, and still valid and quite helpful or so. And so this is also work which we did in the framework of a European Union project. Since also at Sesame, the impacts might be a little bit different or so in that setting, and because of the nature of Sesame than, for instance, at a national facility like I'm working for. Yeah, so I'm coming already to the conclusions. Socioeconomic impacts. So clearly, they have a critical scientific mass, and they generate strong impacts on science, human, social capital, economy, and society. So this is without any question, it is there. And they are a driver of also technology and innovation, yeah, and a driver of training and skill building. However, the analysis and the demonstration, the tangible demonstration of such impacts is nowadays a must. So we cannot say, yeah, we are not interested in that and so on. No, we think as a facility, we have to look into that. We have to set up our structures also that we are able to deliver such such documents and such data. It is challenging, time consuming, but it needs also a well-defined and clean conceptual framework. And there are various frameworks existing, various ways to do it, various approaches or so, but one has to stick to something and say, okay, this makes sense. It is also adequate. At the end, it's not a hard science thing. Yeah. There is permanent challenge of scarce, incomplete, or ill-defined data, which are maybe not so meaningful or so. And this needs really to tackled on from the beginning, that one works on the impact-oriented monitoring, that one looks really at carefully selected, not too many, but several which are significant and which say something about the facility and also easy to collect. Yeah. And of course, this is only what you collect and what you try to work out and to understand, but there is, of course, a true nature of research infrastructures, and there's an entirety of impacts which is there. There's more than we can document and more than we can assess by simply our models and by simply describing it. So there is, let's say, like an iceberg. Yeah, there is something under the water which we don't know. There's much more coming out of this. Yeah. This cannot be done only by quantifiable indicators alone. Yeah. So at the end, we need, and this is also important, we need good case studies. We need really examples where, for instance, a kind of scientific discovery turned out into really something, yeah, or where we can say that this technology at this company XY has really, and this cooperation with the company has really helped them to develop a new product faster. Things like that, and the description of this, a case study, which is extremely helpful because it captures much more of the nature of the various pathways, how outputs from facilities turn into impacts. And with this, I'm at the end of my, almost at the end of my talk. So I have some literature here at the end. Economics of Big Science. There are two books. Actually, this is coming out from the CERN communities, but a lot around it. There's also facilities in ESAF and so on. So these are interesting books. Then there is this guidebook for socio-economic impact from the RI path. Technopolis study I have it, and there are many more which I did not put. And if you would like to look into also the DESY Fraunhofer, which we did with Fraunhofer together, the Petra 3, Petra 4 study from 2 years ago, almost 3 years ago, that's also referenced. And thank you so much for your attention. I hope you found it a bit interesting, and I'm, of course, happy for any questions. Thank you.
Thank you so much, Dr. Frank, for your presentation. And of course, we have many questions in the chat. I will start by the first question. So nowadays, with the development of the synchrotron facilities, could you please provide us a link for these guidelines or handbook and literature's reviews package?
Yeah. So what do we do with these talks? Are they posted on the website? I don't know really. I'm sorry for
Yes,
my ignorance.
sure. If you send us your slide tomorrow, it will be
Okay.
uploaded on the website.
Okay, good. Yeah. So we can, I mean, this RI path is very nice. It has a guidebook. It describes this a little bit. So the methodology I have presented a little bit, but very interesting is the indicator part. So where you can look into the catalog of indicators. Yeah. Mhm.
Thank you so
Okay.
much. So we have here a couple of long questions actually from.
Oh,
So I will try to unmute her so that she can address herself these couple of questions. Sonia, can you try to ask your questions to Dr. Frank? You are unmuted, so you can speak. Hello, Sonia?
yeah, Sonia. I read the question here.
Yeah. Otherwise, I can
Mhm.
read them. So as you prefer, Professor. So we can start with the first question of Sonia. What would be the do nothing counterfactual to say Petra 3? No upgrade to Petra 2, different upgrade, some other investments elsewhere.
Yeah. So probably Petra 3 and Petra 4. So existing is Petra 3. This is running. It came into operation 2009. It was at that time the leading synchrotron. So we run at high energy at 6 GeV, and we have a very large footprint, a circumference of 2.3 kilometers. So comparable is ESA F, but also Spring 8 in Japan or in the US, the APS. Now we see the need to upgrade it because everybody goes into the low emittance lattices and so on, and we have to really have pencil-like beams, yeah, and diffraction limited. So this is the state of the art. We increase the intensity by that. So there is for us, no alternative to it. No alternative because we would like to have more throughput. We would like to have more capability in imaging, for instance, in also looking at hierarchical structures, in also producing faster results. Yeah, so semiconductors is, for instance, a big topic in the moment. So if you look at chip scanning, yeah, so you have a factor of 50 or so in terms of speed and also in terms of resolution, yeah, which you need nowadays. So for us, for our perspective from the lab, there's no alternative to the upgrade to Petra 4. So, I don't know if this answers your question a little bit.
Yeah, I think so.
Okay.
We have a question from Zahid. Looking at the global landscape, which large research facility outside of DESY do you think has done the best job in demonstrating and communicating its socio-economic impact, and what can we learn from them?
Yeah, so Yeah, there are many. I mean, the diamond study, I like this really from the UK. They have very early on started with that. There was a pre-study on that, and that's a it's a very good study. But there are other people. I mean, in terms of data, also ESAF is doing a good job. Yeah, so they have also a good record of all their outputs and so on, and also have various studies. So you hear tomorrow, I think, also from Ed Mitchell, the industry part or so. So he will probably make. They have good case studies also. Yeah. Um, yeah, and then in the US, yeah, clearly, so I don't know if there's a best job. I don't know if we have done the best job, but at least we have politically, we have convinced, nowadays, I would say, we have convinced our government. But in terms of otherwise, I think there are many good studies. Yeah, the astro community is also quite advanced. Yeah, SKA, this is the square kilometer array. They have done fantastic studies. Yeah, and CERN. Yeah, CERN has done this for LHC in depth. Yeah, they have in particular pointed out the very strong factor of cooperation with industry. That industry really, that CERN is like a platform for industry also to learn new procedures, to improve also their technology. So this is quite fantastic studies also, yeah, which CERN has produced.
Thank you. So we have another question from Sonia. More
Mhm.
sophisticated question. Why do you think that scientists who measure things for a living are often so skeptical about measuring their own outcomes and impact?
I okay. Okay, I'm just looking where this question is. So why do they? So now I have it more philosophical. Why do you think that scientists who measure things for a living? For I don't know. I don't know really. I think we should um, the skeptical in a sense that they I think it's also important to have some accountability and to understand what is going on with the results and with my data also and with my analysis. So that's also part of maybe scientific responsibility to understand also and to think a little bit about potential pathways, yeah, how this could really affect others or how this could really manifest into something, yeah, apart if it's really theory or basic science or so. I think one needs to discuss this more with people in communities or so about it, and also show some examples, and then people are maybe getting thinking about this. The more people think about it, the better you produce at the end impacts. Also, yeah, I'm sure about it.
Yes, sure. So thank you so much, Dr. Frank, for answering the questions. And I think today we may conclude. So we have seen how synchrotron techniques continue to transform diverse fields from understanding
Mm,
biological structures to probing Earth's process, and how these scientific tools connect communities and culture through collaborative research. And
mm.
so we can conclude today's session. And I want to thank all our speakers, participants, and organizers for their insightful contribution. And I look forward to tomorrow's session and all the discoveries that can come with it. Have a nice evening and bye-bye.
Thank you. Thank you.
Thank you.